in many scenarios, people are in a strategic situation where first some player moves, and then the other player observes the first player's move and then respond. Okay, so you can actually think of the game of chess. Chess is exactly like that. So first, player one is going to make a move, then player two is going to observe player one's move and then respond to it, and then player two is going to player two is going to make a move, and then player one is going to make a move. So they alternate, and they take alternate turns, and at every step they observe the history. Okay, the history of whatever has happened, and then they decide their next move. Okay, so this is kind of a different game compared to the game that we studied in the last class. Okay, so how do you represent this type of game? Okay, so we'll learn how to represent this game formally. Okay, we'll also learn how to represent this game in the form of a tree. Okay, like in picture and the formal definition of an extensive game. So you don't have to worry about the formal definition if you have some trouble understanding the notations. I'll just introduce it, but you should focus more on the solution concept that we are going to use to solve this game. And plus, I'll give you the definition of a strategy, which you should be you should be very careful about. So I'll spend some time on it, okay, so that you get an idea about what a strategy means in an extensive form game, and then I don't think there'll be any problem. Okay, so let's do and of course there are lots of economic examples as well. You can have a quantity competition game, where firms move sequentially. Let's say first firm one moves, and then firm two observes what firm one has done and then respond to it. Okay, so you can have a quantity competition game like that. You can also have a public good contribution game in a sequence. Let's say first player one do the contribution, then player two observes player one's contribution, and then respond by doing some contribution. Is that okay? Okay, so let me start with one very interesting game. I've also posted this particular game on Piazza. Okay, so I don't know if you have read it. This is a game which I posted as how will you introduce how do you introduce game theory to a 10-year-old. Okay, so I'm also going to introduce extensive form games to you using that particular game. Okay, which is actually a fine example about how to think about strategies in extensive form games, and and then how to just use that idea to talk about the games that are more relevant, in the sense that the games that have a lot of economic uh, applications. Okay, so let me first talk to you about that particular game. So let us say you have 20 matchsticks on the table. Okay, 20 matchsticks. 1 2 3 4 5. 1 2 3 4 5. 1 2 3 4 5. 1 2 3 4 5. Okay, so one of you have to volunteer to play this game with me. I'll tell you the rules. Okay, so anybody wants to play this game with me? So the game is as follows. Okay, so the game is as follows. Whoever one of us, so it's a two-player game. One of us, player one and player two, so whoever is going to play with me, he can decide whether he wants to be player one or player two. So first player one is going to move, and he's going to choose to pick either one matchstick Okay, so he's going to pick either one matchstick from this pile or two matchsticks. So basically the actions that player one has are, pick one or two. Okay, fine. And then player two do the same thing. Okay, so after player one has played, then player two is going to do the same thing. He's going to pick either one matchstick or two matchsticks from the remaining matchsticks. Okay, so let me just show you an example. Suppose player one picks one, then 19 will be left, and then it is player two's turn, and let's say he picks two, then 17 will be left. Okay, so and then this is something that will keep on happening. Okay, so first player one is going to do that, then player two, then player one, then player two, then player one, and whoever is going to pick the last matchstick will win. Is that okay? Understood? The game is clear. Okay, so anybody who wants to play this game with me? So are you playing?
Yeah.
Okay, so fine then. So is playing. So whenever is going to move, I'll use the red color. Okay, whenever I'm going to move, I'll use the black color. Okay, now you want to move first or second?
I'm thinking. I think it will be important in this to be okay. I'll choose randomly. I'll go second then.
You go second. Okay.
Yeah, I mean, I'm not thinking right now. I'm just yeah, randomly. I'm saying second. Yeah.
Okay. Okay. Fine. So let me move first. Okay.
Uh,
So let me do this. So I'm going to cut two of them. Your turn.
uh, I'm also gonna go for two.
Okay, you're going to go for two.
Yeah.
Okay, I'm going to go for one.
I'll go for one.
Okay, you're going to go for one.
Mm-hmm.
I'm going to go for two.
Mine too as well.
Okay, you're two. Okay, I'm going to go for one.
Mm-hmm. I'll go for one as well.
Okay, you want to go for one? Okay, let's see. I'll go for two.
I'll also go for two.
Okay, I'll go for one.
Now I'm caught. Okay. Okay. Yeah. So was playing first was important here, or I think.
Uh, Actually, it was not that important. Playing first wasn't that important. It was so if you have 20 matchsticks, then playing one first was important. Okay, but if you have
Mhm.
21 matchsticks, then playing two is better. Okay, so that is why I'm saying that it totally depends on the number of matchsticks. What is a better position. Okay,
Mhm.
so so in this case, the one who is going to move first will win. Okay,
Mhm.
provided he
They
understands the
play
game.
optimal strategy.
Yeah, provided you play optimal strategy. Obviously you can lose from any number of matchsticks. That's possible, if you don't play optimally, but in this case,
Mhm.
if you play optimally, and you are player one, and if you play optimally, then you will definitely win. Okay, uh,
Mhm.
so so basically when you gave me the first move, you lost the game at that time. Okay,
Okay.
yeah, so I'll tell you, like, so it's actually not that difficult to see what's going on in this game. So if you just think from backward induction point of view. Okay, So
Yeah, that I thought last player should, if you have to win, then you have to give other player when there are three sticks. That I thought, but I couldn't
okay,
go back from there.
okay. So well, so you could figure out for three. I tell you, like how you can just extend this to any number of matchsticks. Okay, so I mean, that whoever is going to move at three will definitely lose, right?
Yeah.
Okay, so I'm going to just put losing positions. So basically, losing positions are those positions where player, if he's going to move, he's going to lose. Is that okay?
Okay.
Provided the opponent is playing optimally, obviously. Okay,
Yeah, yeah.
and put winning positions. Okay, so player
Hmm.
at these positions will win provided he play optimally. Okay,
Hmm.
so obviously, if you have one matchstick on the table, then that's a winning position, right? Player who is going to
Yes.
move at will win because he's just going to pick one and he's going to win.
Yes.
If there are two matchsticks on the table, player who is going to move, at this state, when there are two matchsticks on the table, will win, right?
Yes.
Three is a losing position because no matter what you do at three, you will give a winning move to the other player. Basically, you will make sure that the other player who is waiting, will get a move at two or one. If you pick one, the other player will get a move at
Yes.
two. If you pick two, the other player will get a move at one. So three is a
Hmm.
losing position, right?
Hmm. Hmm.
Okay. Now, what about four? So just think about it.
Four will be winning. Winning.
Exactly. Four is a winning position. You can. So basically, you can think of three as a new zero,
Hmm.
right? Three is a losing position, like zero is a losing position. Similarly, three is a losing position. So you can think of three as a new zero. So you can just ignore this. Okay, so it's like you're starting from here. Okay,
Hmm.
so whoever is going to pick this fourth matchstick will win, right?
Yes.
Okay, so it's like fourth is the last, fourth is a new last. So that's how you can think about it. Or otherwise you can just go backwards in this way. Okay, so four is a winning position. Similarly, five is a winning position and six is a losing position. Seven is a winning
Okay.
position. Eight is a winning position. Nine is a losing position. 10, 11, 12. So you can just move it in this way, and you can see that all the losing positions are multiples of 3.
Hmm.
Okay, is that fine?
Yes.
Okay, so this is how you can just do the inductive reasoning backwards and figure out which one is a winning position, which one is a losing position. Okay, so if you play optimally and you are at one of these winning positions, you will win. So 20, because it's not a multiple of 3, is actually sitting here, and you gave me a move at 20. So I crossed 2 and gave you a move at 18. And when you got a
Hmm.
move at, you crossed 2 and I crossed 1, and then I gave you a move at 15, which is again a losing position.
Hmm. So I cannot reach a winning position. Like I
Yeah,
cannot give you a.
you cannot, because if you pick 1, I'll pick 2. If you pick 2, I'll pick 1.
Hmm.
No matter what happens, I'll make sure that you move at a multiple of 3.
Hmm.
Is that okay?
Yes.
Okay, so I mean, this is kind of a simple game, but you can actually play with your siblings and surprise them every time by winning. Don't tell them the strategy, and let them figure out. Okay, it's going to be fun. Okay, is that fine?
Yeah.
So this is an example, a simple example of a game where player one observes player two's move and player two observes player one's move, and then the game continues like this, and you want to come up with a solution to this problem. When two players who are rational. Rational means who have an understanding of the game, who can do the backward induction, who can play this game optimally. If two such players are going to play this game, then what will happen? Okay, so again, in economics we assume that uh, the agents are smart enough to think in their own interest, and they can also think from the perspective of the other players, because the entire game is common knowledge to both the players. So if it is common knowledge for both the players, they can actually step into the shoes of each other and try and think the game from their perspective as well. Okay, and because both are rational thinkers, they can actually think the way the other player is thinking. They can also think the way they are thinking. Okay, so it's basically when two rational players are going to and they are motivated by maximizing their own interests or utilities. If two such rational players are going to interact in an environment like this, in a game like this, then what will be the outcome? Okay, so that's what we are interested in. Is that clear to everyone? Okay.